Projectile example number 2. We drew a little diagram, which I expect you to do, as we've been doing with any kind of accelerated motion problem, uniform acceleration. And then you're going to split the problem up. So here's the technique. You're going to split up into horizontal and vertical parts. Every time the horizontal is going to be V, S, and T. These are all sub-x's. You don't need to put that on there, but V sub x, S sub x, and then T is consistent, or the connecting link between the horizontal and vertical. So we have V sub I vertical, V sub F, A, S, and T. And A will be negative 9.81 meters per second squared. Now the question is, where does the 22 go, for V sub x or V sub I? And the answer doesn't go in either of those places. We have to find components, and that's why we've spent some time figuring out components of vectors the last few days. You're going to have a V sub x, then that's V, which is 22, and then V sub y. And then we can make a rectangle if you want. And this is 35 degrees. Alright, if I look at this black triangle, and there's the right angle, and I know V is 22, if I take the cosine of 35, that's going to be V sub x over V, and V is 22, the hypotenuse there. So V sub x will be 18.0 meters per second. So that goes in my horizontal table over here, 18.0 meters per second. And then we use the sine function of 35, because this is V sub y, is the same size as V sub y, but the sine of 35, that says 35, equals V sub y over the hypotenuse of 22. So V sub y is 12.6. Once again, we can go to 3 sig figs. If you want to go to 2 sig figs, probably better. But where does that go in the table? Well, that goes into V sub I vertical. That's 12.6. 12.6. And it's important that that's positive, because the ball is being thrown in the upward direction. Alright, so we have the components, and this is going to happen a lot of times with projectiles. You're going to have these components like this. That's one of the first steps you're going to be doing. You'll be doing in many problems. Now the other tricky part here, and we've got to read it within the context of the problem, because it tells you that in part A that the ball is going to travel and be caught by the receiver at the same height it was thrown. And here's the tricky part. That means that S will be 0 meters, the vertical displacement. The horizontal displacement, S sub x, which is going to be from the quarterback to the receiver, S sub x is not going to be 0, but S sub y, vertical displacement in the vertical portion of the table over here is 0 meters. 0 meters. So now, once again, you can maybe see where this is going. We want to figure out the time of flight, and we could also figure out V sub f over for the vertical. Now you can play around with all 4 of the uniform acceleration equations for the vertical variables here. But if you look at the 4th equation, something interesting happens, which you may or may not have been able to predict. Let's see here. The 4th equation is V sub f squared equals V sub I squared plus 2as. But if you try to plug in there, you get V sub f squared, which is what we're looking for, equals V sub I squared, which is 12.6 squared, plus 2 times negative 9.8 times 0. Well, you simply get V sub f squared equals 12.6 squared, and 12.6 squared is 159. So then V sub f is just the square root of 159. But it's, once again, and here's where your math background comes into play, V sub f is going to be the plus or minus square root of 159. So it's plus or minus the square root of 159, which is plus or minus 12.6. Well, now I got to use the context of the problem. The final velocity of the object will be negative 12.6, not positive, because the ball will be coming in the downward direction when it's caught. Which, if you just think about this, anytime you throw a ball straight up, it'll come back down with no air resistance. It'll come back down at the same speed as you tossed it, but the direction is the opposite, so that's why it's always going to be negative. It'll always be the case if you're catching something or throwing and catching something, it comes back to you at the same height. So now the problem becomes pretty easy to figure out the time. You can pick any one of the other three equations to determine the time that the ball's in the air. So if you want to figure out t, I'm going to take the first equation, which is one of the easier ones. That is v sub f equals v sub I plus at. V sub f was negative 12.6 equals positive 12.6 plus negative 9.8 times t. Solve for t, you're going to get negative 25.2 equals negative 9.8 t. T will come out to be a positive number. And if you ever get a negative number for t, you know you're doing something wrong. But t comes out positive here. It's positive 2.57 seconds. So that's the time of flight. Now we can go to the horizontal conditions to figure out how far the pass went horizontally. Once again, v sub x, or just v in the horizontal direction, is s sub x over t. V sub x is 18.0 meters per second. Looking for s of x. T is 2.57 seconds. So you simply multiply 2.57 times 18. And that is 46.3 meters. That's quite a toss because that's right around 50 yards. That's a pretty good pass. Now we need to figure out how high the ball was at its middle spot, which is the highest point in its trajectory. We have a couple of ways we can do this. What I would do is reset the vertical conditions. If you go back to vertical, and you have v sub I, which is 12.6 meters per second. But v sub f of 0, okay, it'd still be moving horizontally at the 18.0, but at the high spot, the v sub f is 0. A is still negative 9.81 meters per second squared. S will be some number now, and t will be some other number. And t, you can figure out, you can take a shortcut, it's going to be half of the 2.57. But say, assuming you didn't know that, you could do the fourth equation, v sub f squared equals v sub I squared plus 2as. You don't need to know what t is. But v sub f is 0 equals 12.6 squared plus 2 times negative 9.8 times your s. Solve for s. S comes out to be 8.1 meters. But when the quarterback threw the ball, it was already 1.5, if you go back and look at the problem, 1.5 meter release point from the toss. So that's 9.6 meters total from the ground. That's the total height of the ball in the middle of the path. Finally, part C. At what speed does he catch the ball? This was part B. At what speed does he catch the ball? What is the magnitude of the speed? Well, the shortcut here is it's the same speed with which you throw the ball. If we have symmetry in a problem, which we do, because the horizontal component never changed. If you're catching it the same height as you threw it, your vertical component is still 12.6 but negative. The overall velocity with which you catch something is the same as the overall velocity with which you throw it if it follows the parabola and you catch and throw at the same height. So the answer is just 22 meters per second. That's answer C.